Good morning, everybody. This is going to be a very exciting class. I think we still have a few more fundamentals to deal with before we can start looking at the stars and the galaxies. We need to finish up our, reconciliation with the state of the composition of the sun today. But we're going to that discussion leads us nicely into how the stars are powered. So we're going to start talking about the science of fusion a bit. It's a fairly cursory overview that we get into in this course. Of course, nuclear science is, a very complex, nuanced art, and so we'll talk about some of the basic reactions today. And we're basically talking about our star because, of course, that's the one we know the best. But, some of these, we'll find out in the coming weeks, some of these bigger stars are doing much more complicated processes, especially in terms of making the atoms that we see in this room around us for the most part. So our sun is essentially only capable of fusing something as small as helium. And I doubt there's any helium in this room, mainly because the Earth is running out of helium. So that turns out to be a serious problem. Now there's some hope we're going to be able to get some from the moon once we start going there. But it's becoming more and more expensive because we don't have much of it. But we do have lots of other stuff like carbon and oxygen, mainly. And of course we have nitrogen in the air. But these big, heavy these big, heavy atoms, they need a bigger star in order to be made in. So we'll get to that. But first we'll start with our sun. So before we get there, let's grab some attendance points here. So I'm going to randomly call some folks. I marked the people that I spoke to this morning down already, so I'll leave you guys alone. And I appreciate everybody who came and hung out this morning. This has been promising, so maybe we'll try it again next week. Randomly, cool. Do you remember anything that was any curiosities from the last class, or something you remember, or some question you had, anything like that? Yeah. So the solenoid system, basically. This turns out to be the way that it seems like nature organizes its own giant magnets, right? So every atom has let's say every simple atom that has some conductive abilities also has the ability to be magnetized, right? And so these simple hydrogens, like our star is made out of, if they get currents running through them, right? If they're aligned properly and conducting motion amongst the groups of those atoms, then they can also have coherent magnetic fields that develop magnetic properties. That's the equatorial motion of that electron shell, that surface of the atom. We're going to talk more about the atom today, so I'm not going to bore you with the details because it really matters when we start talking about fusion and we start talking about, actually, this week's chapter in your book goes into the different elementary particles, and so we'll come back, swoop back on that. But needless to say, the coil is a beautiful organization where you take all of those aligned atoms and you align all the equators even more along the sides of the coil. So all that equatorial magnetic motion is conserved, and you get a more powerful, coherent, shared magnetic field. It's a really amazing, just sort of accident of nature. It's pretty cool stuff. So that's happening under our feet in the molten conductive materials under our feet, generating our magnetic field, which, by the way, if you weren't here last semester, we can thank that magnetic field, that magnetic ability of those atoms, their extended magnetic abilities. We can thank that coincidence for essentially everything that we have on Earth, because without it, we wouldn't have an atmosphere. We would be getting, all of our DNA would be getting destroyed by cosmic rays. And so the magnetic fields are a really, really important piece of being alive here on this planet. All right, thanks, Romy. All right, let's do a couple more. How about Matthew Forsyth? You here? Very good. How about Matthew Van Dyck? Van Dyck? Nope. All right, how about, that's me. How did I end up on this list? All right. How about, so the Solarians, Herschel and the Solarians. So that was not that long ago. That was maybe 200 years ago. and seriously entertained for quite a while. We didn't have time to finish the entire history of that discussion, but I did want to read you guys some quotes so you get a sense of really just how much disagreement that was quite jovial, right, and congenial. People had very different ideas about the sun, but they were discussing them. Having a career as a scientist wasn't a thing until about the 1950s. And so with the rise of career scientists, it's in some sense become more difficult to move the needle about theoretical understandings. Back in the 1800s, early 1900s, it was really just people with curiosities who were corresponding to these societies. They didn't have any money at stake or anything like that. Of course, most of them were wealthy to begin with, and so it was limited to a special class of people, and there's downsides to that. But you didn't have the same constraints on what you could do. For instance, if I want to, say I'm a professor, well, I am a professor, but say I'm a research professor at like a big research institute, and I have a lab and we're doing experiments. Well, I have to ask for money to do those experiments. And that's a great system because, of course, in some sense, it vets who's doing the most productive research, but then you have to ask what constitutes productive, right? And so it turns out that what we do is we fund a lot of technologically promising science in this country, which is great because we have, cell phones and video recorders and everything. It's really, really useful. But when you have very theoretical ideas, say about fundamental basic atomic science or about fundamental basic biology, let's say you have sort of outlandish ideas about it that might be revolutionary. Those are very difficult to fund, actually. So you can't really promise anything from those immediate new revolutionary insights. And so there's a lot more gum in the wheels these days in terms of moving these things forward. But that wasn't the case back in the 1800s. So people were exploring everything from the sun having these sunspots being clouds, then to the liquid surface of the sun. A huge problem that we didn't get into last time is that with the sunspots being holes and with the idea that the density of the sun was so low that people thought, well, it has to be a gas. The next problem was, well, if it's a gas, why can't you see through it to the other side through these sunspots? That was a huge, huge problem, actually. Still a problem in some sense. And, the solution that was offered later that I didn't get to by this Jesuit priest, his name was Father Secchi, was that there was some sort of condensed matter that was like dust that was dispersed throughout it that was leading to the thickening. But many ideas were tried on, and we'll continue with that in a moment. Let's get one more person to chirp in here. Yeah, we'll talk more about that today, because the funny thing is where all of these discussions lead to is the question of how is the sun powered, right? And this convection process plays into that. The fact that it even has layered structures, right, is a necessity of there being this opacity problem. You can't see through the holes, so there must be different stuff down below than what's on the top. There must be something interceding. So convection cells are really important. They're also really important in the generation of a magnetic field too, and the sun has a really strong magnetic field. In some sense, the convection is half of the story of what organizes those solenoid currents that give us that consolidated, coherent magnetic field. So yeah, convection is really interesting, and it's something you're really familiar with. If you ever boil water or cook on a stove, you can see things. You can see the rising cells actually, especially if you ever something with color. It's easier to see the actual convection cells, these little rotating things. Sometimes you get 2 or 3 of them inside of a pot. So it's a very commonly observed phenomenon. All right, very good. All right. Let's do one last person, and then we'll cruise on and get ourselves towards fusion. Nietzsche, yeah. Yeah, Nietzsche is he's a character. Have any of you guys read Nietzsche in any of your other classes yet? A little bit. He's one of those, I think crazy people are some of the most interesting intellectuals in some sense, because they always have, we were talking about this before class, there's these lunatics have really good ideas sometimes, but they have a lot of really bad ideas. And in my opinion, Nietzsche kind of falls into that. He sees the world as being organized exclusively in terms of power dynamics, which I think is a little psychopathic because, if you guys all grew up in families, I'm sure, and if you exclusively view your relationships, or with your friends, say, in your dorm or whatever, if you exclusively view all those relationships through the lens of power, like, what is this person trying to get from me? You end up in a really paranoid, bad state of mind. And I don't think that's the fundamental unifying feature of humanity. But Nietzsche had some really brilliant ideas too, and one of them, I think, is the eternal recurrence idea, which, given enough time, will events repeat themselves? Or can we keep coming up with new configurations of the universe forever? I don't know. It's an interesting thought experiment. Okay, cool. Last thing I want to say, just business-wise, assignments are always due on Saturday. I'm not really tallying zeros. I'll probably do it at midterm because I'm going to get requests from people's athletic groups and stuff for how your grades are. The assignments, the video assignments, definitely turn those in on Saturdays, and send me an email if you turn it in late so that I can score it. And then, what else? I think that's about it. So let's cruise on along. All right. We will finish solar history to the extent that we need to at least overview the 5 pillars of the gaseous sun that we're stuck with today, and try to understand why we're stuck with those. So, to be perfectly clear with you guys, the Greeks, let's just summarize this. The Greeks thought of the sun as, or at least the few Greek rational philosophers thought of the sun as this burning hot ball of metal, which is interesting. That was not particularly popular after the Enlightenment. Nothing happened during the Dark Ages, basically. And then in the Enlightenment, that became a little unpopular because people could see that the surface of the sun was changing. It was moving, right? And nobody had ever seen a metal move or change. So this notion of liquid or gas became intriguing. And the liquid thing was very popular for a while because, the stellar opacity problem, like I keep saying, you couldn't see through these sunspots, right? So it seemed like there had to be something that was not exactly a gas, especially since hydrogen's a transparent gas. So today, we think about the sun as a gas too, but we call it this other kind of gas, which is a plasma. Now, plasma is a really interesting term because actually, if you start studying plasma physics, what you find is that the word plasma actually can encompass both gases and liquids. And so it's kind of funny because it seems like what we've done by calling the sun a plasma is we've thrown our hands up to some extent and said, well, it could be either one, right? So a plasma is essentially a conductive gas or liquid, right? It's very, and I'm not necessarily talking about like a salt solution, but it can have flow, like fluid behavior, but it's certainly conductive, right? There's some electrical component, and by virtue of that, there's a magnetic component to it too. So that situation was never really resolved. But what really ended the conversation was the production of energy, how the stars are powered. And the proponents of the liquid sun did not have a mechanism for how the stars could power themselves. And the gaseous proponents did, particularly Arthur Eddington, who gave us the fusion mechanism that we're essentially using today. So we'll take a look at that. And of course, this brings up one of my favorite topics in the world, which we'll get into in a moment, which is energy. So energy is one of the most abused words in the entire English language, as far as I can tell, certainly in all of science. You hear everything from like, how's your energy today, to, I'm not feeling the energy of this room, to this, the energy, clean energy production. So what the heck does this word actually mean? We'll deal with that. That's if you learn one thing in this class, that will be really good for you, and you can go tell your friends. All right. So before we get there, let's check out the 5 pillars. Well, there's really 6. There's basically 5 historic pillars for why we're left with this gaseous plasma, why we believe, why the consensus view is that this star is something of a gaseous plasma. And it's interesting because all 5 of these ideas were situated well before the 20th century. So they're very old ideas, but they were compelling at the time. So the first one was the man who developed all of the blackbody research. Now, remember, the sun has a perfect blackbody spectrum with a gaseous atmosphere that gives us some lines over top of it, some gas lines. What's kind of tragic is that this man, Gustav Kirchhoff, he really wanted this idea of blackbodies and thermal radiation to apply to all atoms everywhere. He was never able to observe this kind of behavior from gases, but he believed that if a gas became significantly opaque, which, under extraordinary pressure he imagined that would be possible, that he could apply his laws. And so he developed, I don't have it written up here, but he has essentially an equation which gives you the temperature of a body based on the wavelength of its peak emission, so where the top of that mountain is, right? And there's a scaling parameter that has to do with how absorptive that material is. And so he imagined that it would be possible to have a gas that was significantly thick enough, significantly absorptive enough, that you could get this out of it. Now, nobody was ever able to do that, but he was, as you can imagine, having derived this relationship, he was one of the most famous scientists of his day, and people went with it. There's this huge push in physics back in the 1800s, and really still today, to be able to unify and universalize your findings. Everybody wants that theory of everything, right? It's the idea that, some relationship can be seen at all scales everywhere. And so he really wanted that to be the case. The problem is it doesn't work out even mathematically in that equation. So there's this factor which essentially compares the absorptivity, how much light something takes in, to the emissivity, how much light it gives out. The problem is there's certain situations with perfect reflecting cavities, like let's say a microwave or a laser, for instance, right? In a laser, you have walls that are basically mirrors. There's a little cavity that the light waves bounce back and forth inside of. And it's perfect. It has zero absorption, those walls, right? The problem is, when you have zero absorption, you can't get any kind of a blackbody curve. But according to Kirchhoff's relationship, you should still be able to get a blackbody spectrum out of those walls of that cavity. And so there's limits at which this mathematics breaks down, and yet we still use this equation as if it's limitless. And so it's a bit outdated at this point. So that's the first pillar. The second pillar is that people discovered that when you squeezed gases, put them under great pressure, that those gas lines, right? Like I said, if we were to put this prism up here, we'd see individual colors. Well, if you squeeze gases hard enough, they do broaden out a little bit, right? So you do get these, instead of having really sharp peaks. So let me just draw you guys a picture here. Blackbody spectrum. Nice, smooth rainbow of colors, right? You're going to get so tired of this by the end of today, but that's okay. A gas spectrum is going to be these individual peaks like this. Really peak, just individual frequencies like this. Oop, that was an ugly one. Individual peaks, right? Now, if you squeeze the gas really hard, what happens is these peaks get a little bit broader, something like this. And so the hope was that, okay, well, the sun's under a great deal of pressure, there's a lot of mass there, and so maybe all of these individual gas peaks can be blended together because they spread out properly, which is an ambitious hope. But another thing was that this gentleman named Andrews started studying different phases of matter, right? Now, Andrews essentially realized that when you get things really hot, they go through this phase where essentially they become gaseous, right? That's how we get into this plasma layer up at the top. What Andrews didn't know is these are really high pressures out here. What he didn't realize is he didn't have access to the right-hand side of this graph, which we developed in like the 1980s. We discovered that actually when you squeeze the heck out of something like hydrogen, you actually get into this strange realm of a metallic liquid, which is really interesting. It's almost like you pressurize the gas so much that it has nowhere to move, right? And it still has all those ionized conductive properties. Its surface, its electron shell is still whirling really fast. It's very electrified. But it behaves as if it's a liquid. It has layers to it, almost like water. So he didn't know about that. They only knew about this side, right? They didn't have access in the laboratory to those early things. So they assumed that under such temperatures, you had to essentially have a gas. Fair enough. And then there was this really old idea of how solar systems formed. This goes all the way back to Laplace and really back to Kant and Emanuel Swedenborg, who these were philosophers from the 1700s. These guys basically came up, which is quite ironic, that they were philosophers primarily, not really even natural philosophers. They just had some ideas that stuck around. They had the idea that a big ball of gas collapsed gravitationally in order to make stars. And that idea has essentially stuck with us for 300 years. I think we may have touched on that the first lecture a bit. So it's interesting that we still use this basic nebular model, which doesn't really, is starting to finally, people are starting to consider things like chemistry and condensation, things like this in the formation of stars, in the formation of planets, whereas it's traditionally been viewed as a gravitational mechanism. Now, this, of course, led to people starting to speculate about how the star was powered. So the natural choice was, okay, if there's gravitational collapse causing stars to be born, well, what if they're kind of like combustion engines where you squeeze stuff and it gets hot, right? So that was a very popular idea, and actually Lord Kelvin, the famous Lord Kelvin, who we get the temperature unit from, came up with this idea of this contractile mechanism, along with this other thermodynamicist named Helmholtz. Now, this was the birth, by the way, at the same period in history, this was the birth of engines for the first time. So this science of engines, which is called thermodynamics, how to manage heat flow and actually get work out of it, was in its complete heyday. It was just like, like AI sciences today, or something that's absolutely brand new and revolutionary. So everybody started thinking about things in terms of thermodynamics all of a sudden. Well, they started calculating on this. Okay, the sun's contracting. It can contract at this rate. It has this much hydrogen. The problem is that during its entire lifetime, it's assumed to have contracted to its present size. Now, what they can do is they can look at the luminosity, the amount of energy that's being shown out of the sun, and they calculated that the sun could only keep shining for something like 100 million years more, right? Now, this didn't make any sense because guess what else was happening in the sciences at the time? Charles Darwin. So this might shock you, but as early as the mid-1800s, in Darwin's day, which was, say, the late 1700s, most people thought the Earth was 5,000-6,000 years old, right? This was actually like the mainstream intellectual position. And so Darwin really shook that up because he said, I don't think so. I think these things take millions and millions and millions of years, if not billions of years, these organisms to develop their shape. And by extension, the geology was to be revolutionized as well. So this idea that the sun only had 100 million years left of heat in it was just untenable. It didn't make any sense. And it didn't make sense in terms of the time scales that would have already occurred in order to, have contracted to its present size from the size of the gaseous nebula that they needed. So that didn't work, okay? Now, we're getting close to the 20th century at this point. And there's an interesting rivalry building up in England. There's these two astronomers. One's name is James Jeans, and one named Arthur Eddington. And it's hard to describe the rivalry that was occurring between these two gentlemen. Can anybody think of any good public intellectual rivalries today? Gosh, I'm going to have to think about that for next time. Anyways, these guys were butting heads constantly. Now, Jeans was a huge proponent of a liquid model for the sun. Eddington was a big proponent of the gaseous model for the sun. The problem was that the only thing Jeans could think of for how the sun powered itself was by radioactive decay. He said there's these things like uranium, which were very newly being discovered and developed that were decaying and powering the sun, which is a good idea. Problem is, very shortly thereafter, people realized that the sun was almost entirely composed of hydrogen and helium to some extent. That means that there's nothing big enough. Well, there isn't much that's there that's big enough to be decaying. Eddington, on the other hand, had this idea of fusion for the first time. That actually, if you squish some simple atoms together, what happens is you make a new atom, but it's a little bit less massive than the original two. And the result of that is that you can do a little bit of work with the excess, really heat and radiation energy that's released. So something changes physically about those two atoms when they merge together, and it's a relaxation process. It gives some work ability, some energy. So we'll deal with that in a second. So, something else was, I think Eddington had going for him as well. Eddington was the first person to really recognize Einstein's rising star, right? So Einstein was a German scientist. He was already quite well known in scientific circles for his work on the photoelectric effect, which is essentially just saying you can get electricity out of light. And we know this, right, from solar power and things like this. Plants obviously know this better than anybody. So he was quite well known in Germany and Austria and in these intellectual circles, but the greater English-speaking community didn't really know about him. And particularly, nobody had any idea about his relativistic ideas, which are still at the forefront of modern physics. And we'll unpack those when it's time. But this guy, Arthur Eddington, actually translated Einstein's works into English. He was also a very popular guy. He was like Neil deGrasse Tyson or Bill Nye or something. He was writing in all of the popular magazines at the time. And he actually ended up organizing the first expedition to prove Einstein right about this relativity business. They actually went to an eclipse and measured the position of the stars as the light bent around the sun. So, Eddington was just in the right place, and he really, this fusion idea turned out to make a lot of sense, and it was developed all the way up through the 1950s, 1960s, and that's where we're at, essentially, today. This idea that you squish two atoms together, it's a relaxation event, right? Something about the entire system relaxes. Now, I think this is, maybe the last lecture that I'm going to bore you with any details about the atom, but I don't think that we can make sense of the stars without understanding light. And if we can't understand, in order to understand light, we have to understand electromagnetism. In order to understand electromagnetism, we have to understand atoms a little bit better. So I think that it's reasonable to think about atoms as being in some way connected to one another, right? And it's difficult to understand that, but there's some analogies we can use. So, you might think right now, we're all being pulled down to the floor right now by gravity, right? Which is, you don't really think about it too much, but it's kind of bizarre. And the reason for that is in some sense that each one of your atoms is being pulled on by each one of the atoms in its vicinity at the surface of the Earth. So these atoms, this network of atoms, right? There's some dissipative process when two atoms are joined together that it actually relaxes the entire network, it seems like. It's actually, if you think about it as like a giant spider web to some extent, you can imagine that all of these connections these two atoms have together, they can now share to some extent. And there's a release. And that release is often called this release of energy, which is captured, of course, in Einstein's famous equation, which we'll deal with momentarily. First, though, let's deal with this concept of energy, because this is a real nightmare. It was very difficult for me to not say that it releases energy, because that's obviously the shorthand for what happens. But we have to understand the word energy before we get there. All right, so this is what your textbook says. Energy is a challenging concept to grasp because it exists in so many different forms that it defies any single simple explanation. In many ways, comprehending energy is like comprehending wealth. There are different forms of wealth, and they follow different rules depending on if they are in the stock market, real estate, a collection of old comic books, great piles of cash, or one of the many other ways we make and lose money. It's easier to discuss one or two forms of wealth or energy than to discuss the concept in general. Yikes, what a nightmare, right? I mean, this is one of the most central terms in all of science, and people are very scared to even try to define it. So let's try to define it, because we can't get anywhere if we don't understand this word. So it actually comes from the Greek word energia, which essentially means activity. And I think that's a reasonable starting place, actually. It wasn't actually, I think Thomas Young, one of the early light physicists, people studying light, was the first to actually coin the term energy. But it went through this whole, before it was called energy, there was this idea that there was some animating force to matter, especially life, right? It was called, they used to call this vis viva. Vis means power, strength, and viva is life, right? So it's like the life force, right? And they actually started to be able to quantify this and compare this to kinetic energy. When something's moving, how much motive force does it have? How much can it actually displace other matter, right? And so the mathematicians went to work on this. Thermodynamicists went to work on this. And this word energy became, in some sense, synonymous with the concept of vis viva. Now, the thermodynamicists realized that this vis viva stuff was the same thing that they were thinking as the ability to do work in their engines, essentially. And so there appeared this idea that work, which is essentially a force, some sort of effort applied over a distance, were the same thing in and of themselves. And they started using the same units to describe this as vis viva, right? They actually ended up using the unit joule. But what happens is that this force being applied over a distance, what does that mean? Like, what is actually happening there? And let's bring Einstein into the mix a little bit now too. So Einstein famously related energy for us here as E equals mc squared. So we have a force being applied across a distance, so some effort being applied across a distance, and we have some mass times some acceleration, some squared velocity. You know, and this, by the way, this equation is very similar to the equation for vis viva itself, right? He's just given it a new name in some sense, and instead of using v squared, he's using c squared, which is the speed of light. I think, you know, what it comes to is that your textbook, even the only reason they even bring this equation in is because they want to show you that mass can be converted into energy. Well, this makes a new nightmare for us because now we have to define that word mass. And most of you will think, when you think of mass, you think of material, right? Some sort of matter, right? But it's not quite so simple. So the word mass is essentially a term that comes out of gravitation. So mass was developed primarily in the atomic age by the chemists because they realized that individual elements had different weights, which is very bizarre. So atoms themselves had different amounts of gravity, actually. So this word mass really only makes sense from an empirical standpoint for atoms themselves. What happens is when we get into things that are smaller than atoms, you also see sometimes people tacking masses onto them. But what they're really doing is they're accelerating those particles through a magnetic field, and they're saying, hey, that magnetic field is pushing them out of the way with this strong of a magnetic field. Therefore, that particle must have an equivalent mass. Its magnetic deflection must have an equivalent mass of this. And so those aren't really true masses in the sense that they're not gravitational, right? They're not gravitationally measured like everything that's made out of atoms. Myself, you, this table, we all have true masses, right? So back to the question, what's this actually telling us? I think what this is telling us, what Einstein's famous equation is actually a definition. It's more of a definition for what energy is than it is any kind of statement about conversion between energy and matter. It's a definition that says what energy means is it means that some material is in some quantity of motion. That's it. Energy just means something moving at some amount. Right? So if you have potential energy, you might have potential energy, right? You have, a candle that you can light on fire, right? and it'll keep you warm. Well, there's a lot of stored bonds in those molecules, right? They're very happy to break apart when you set them aflame. So once that flame is going, now you have a lot of those atoms in an increased degree of motion. That's what heat is. It's the gas atoms bouncing around, right? Heating your body up, essentially. That's converting into this potential to go into motion. Now the atoms are actually in motion. They're energized, right? So if we work back to this idea of fusion with this idea of energy release, what's going on? Well, the traditional textbook is going to say something like, well, those atoms, when they're combined, they convert the missing mass into energy. Now, has anybody ever heard the word reification before? This will be good for you too. You can impress your friends. So the word means, it's a philosophical term. It means misplaced concreteness. So you have this serious issue that happens from time to time where people that are studying systems will, and this happens particularly with geography and so forth, they start studying the map and they get really obsessed with the map. And at some point, they forget that they were actually studying a piece of land in the first place. And they start creating theories based on the map, treating the map as if it is actually the territory itself. Now, this isn't a very easy thing to do in our common language because we use analogies all the time. So I might say something like, I'm feeling kind of heavy today, right? Or it's, try to think of a good one. Well, needless to say, if you want to be very careful, you do want to be very careful in physics, and particularly in physical sciences, because it's very easy to start treating ideas like mass, which is essentially a scale of how much pull an atom is putting on one another, and start treating mass as if it's an actual object, a body that I can move around the room, right? I'm going to take this mass over here and move it here and do that. But that's actually a conceptually and linguistically flawed way of looking at the word mass. You can't actually move mass around. Mass is an idea. You don't move ideas around physically. Now, you can move an atom that has a particular mass. That's a quality of the atom. But you can't move the quality around. And so the problem with saying that you can convert an idea, like energy, into a material, like matter, this is very confused. What it's actually saying is that the material can be accelerated, in this case, the limit being the speed of light, and you can get the maximum amount of energy out of a material by accelerating it. The material possesses mass. That's a quality by which we scale how much material is there. It's a good proxy for how much material is there, mass, right? But ultimately, there's some material, it's going into some motion. The limit of that motion is the speed of light. Now, why in the heck is there a speed limit on light? Any ideas? No, I think that it's not a measurement error. I think that it appears to genuinely be that, well, for instance, if there was no speed limit on light, we should be able to see different wavelengths of light moving at different speeds. But all light seems to travel at the same speed. It could be a big, fat radio wave. It could be a really jittery gamma ray. It doesn't matter. They all seem to go at the same speed. And this is actually quite easy to study at this point. You can you can measure it in lots of different ways. The easiest way is sort of the same way that the cops clock your speed on the highway. They bounce some sort of light off of you and see how long it takes to come back, and then deconvolute the distance and so forth. But it is constant. It does seem to be constant. Now, what's interesting is that actually waves in all materials are constant. So if I hit on this table, there's going to be a sound wave called a phonon. It's going to travel through this, if I put a pickup at the other end there, and I can measure it, a little contact mic, there's going to be a characteristic sound for this sound wave material. And that's defined largely by how difficult it is to move the lattice of that material, right? Do you guys know what I mean by lattice? I mean, basically, the cage of atoms inside of this material. How easy is it to displace it and bend it? How stiff is it? How dense is it? Those things matter. Those are going to change the speed, right? Now, it turns out the more stiff it is, the faster the speed is, actually, right? And so gases, they all have characteristic speeds of deformation, of wave, of displacement inside of them. And so, I think that we can learn something really interesting about whatever medium might be, whether you call it space-time or you call it whatever you want. You could call it the atoms themselves. The rate at which they're capable of deforming seems to be inscribed by the speed limit of light itself. It's telling us something about we're dealing with a really stiff, these atoms are very stiff if the light is in fact a deformation of those atoms. Or we could think of it as space-time, right, which is the popular terminology these days. Space-time is extraordinarily stiff. It's actually unimaginably stiff. There's a guy at Princeton named Kirk McDonald. You can check out his papers. He's written a few different ways of calculating the stiffness of space-time, but it's, dozens of orders, let's say 10 or more orders of magnitude stiffer than steel is the projection. And so the speed of light tells us about that speed limit. Anyways, material in motion gives us energy. When we squish these atoms together in a fusion furnace, like at the heart of the sun under extraordinary pressure, gravitational pressure, certainly, what happens is that whole system relaxes, and you get any number of events that result from it. And we'll break apart the different fusion reactions here in just a second. Let me make sure I don't have anything else to say about the atom. Questions at this point? I know I'm throwing a lot at you guys very quickly, but this is our last chance to deal with the fundamentals before we start talking about big objects. And so if we don't understand the small objects that make up the big objects, it's going to get really abstract really fast.
So light is the ultimate speed limit, right? Is there anything that could go faster at all, like gravity or anything?
Gravity is really interesting. It travels at the same speed, right? So that's the common wisdom at the moment. Could anything go faster? I think that answering that question really comes down to understanding what, like I was talking about, why does light, what is the medium by which light is propagating? If it's space-time, is it possible to take an atom outside of that medium, outside of space-time, let's say? Now, I kind of cringe at using the word space-time for a medium because space-time is an idea. And see, I'm guilty of this reification when I do that, because I'm taking an idea and I'm treating it like a material. The reason space-time is not a material is because it's dynamic. It involves motion inherently. It has time involved in it. It's an idea. It's a concept to describe a movie, right? But whatever medium is conducting light, right? Whatever is deforming, could you take an atom outside of that medium? Could it be disconnected from its neighbors? Can you gravitationally disconnect atoms from their neighbors? There's a lot of people in the fringe propulsion world who are dreaming of being able to make, serious people too, right? I know there's at least one patent on the books for the Department of Defense through the Office of Naval Research for an anti-gravity device, right? You can go read about it. There's this guy named Salvatore Pais who's patented an anti-gravity device for the ONR, for the Office of Naval Research. No one's ever built it, to my knowledge, but people take these ideas seriously. And as far as I can tell, the only way that something that would be working against gravity would have to somehow disconnect those atoms from from the network, right? They have to unplug. So, maybe in some sense, the reason that light travels at this speed limit, the reason objects can't go faster is because they're embedded in this same network. And deforming that network can only be done at most at the speed of light. You can't get just like I can't make a sound wave go faster in this medium than it already goes unless I change something about it fundamentally. right? Unless I dissolve it or make it thinner or something, right? If you can somehow take the atoms of the spaceship and disconnect them from the rest of the universe, maybe. That's your only hope. I have no idea if that's possible or not, but that's the only thing I can think of. But yeah, seems like as long as your atoms are connected to everybody else's atoms around you, you're not going to go faster than it takes to displace all that stuff that's in the way, basically. And so all these speed limits can be thought of as literally the time it takes for those atoms to rearrange themselves as the wave passes by. That's how this works, right? This wave is traveling down this table. It's actually radiating out in all directions. And those atoms have to get out of the way as they wobble and move. And so any wave in any material, whether it's a subatomic substance, call it whatever you want, you still have to displace the subunits in order to have that wave propagate. If it's a stadium wave, right, people still have to stand up and sit down. That takes time, right? The whole thing takes time. And the material characteristics tell us about what that speed limit is. So the future is wild. I mean, it's been kind of interesting actually watching the news this last year because it seems like there's been these congressional hearings on UAPs and so forth. You guys seen any of this? I don't know what to make of it all, but it seems like, and there's these aircraft carrier pilots who are seeing these little TikTok things that were disobeying physics and so forth. I don't know. I don't know if it's just a big cover-up for something the government, some new military aircraft they're working on or whatever. That's usually what it's been in the past. So the UFO craze was going on in the 80s. It turned out they were working on the stealth fighters and stealth bombers at the time. Maybe it's something like that. But anyways, people are taking these kind of far-out propulsion ideas very seriously, especially after those TikTok videos came out. I did, however, I have to break people's hearts about this TikTok stuff. Around the same time that happened, there was a little seen article in Forbes magazine that was reviewing this defense contractor who had developed this holographic projection system that was capable of projecting a hologram from a satellite with a heat signature that would show up on pilot radar. And they had like a big diagram. You can go look up this article. It's very fascinating. So I don't know. Maybe not really spacecraft. Maybe just holographic projections. Some sneaky Defense Department business. But anyways, people are taking it seriously. They're thinking about alternative forms of propulsion and anti-gravity and all of that. All right, so the next thing that your textbook brings up is these different subatomic particles, and they do that because we want to talk about the nuclear reactions in the sun, and the result of these nuclear reactions is the production of different subatomic particles. Okay, here's the problem though, folks. If I ask you, what do you think, can somebody tell me what a particle is? Anybody? Don't be scared. Not a subatomic particle. Let's say I just mean a particle. What's a particle, right? I'm sure you guys are thinking a particle is just like a little chunk of something, right? Like probably some particles of dust here from this chalk, right? Little pieces of something, right? The problem is that this word in fundamental physics does not mean a chunk of stuff. And that is a serious disservice, and it's a real nightmare, actually, because people can get all the way through PhDs in theoretical physics and not really totally sit down and think about this for a second. So subatomic particles have intrinsic momentum to them. They represent a measurement of a system that reveals something about the motion of that system. So I guess it's a good time to bring back this concept of reification. Because what's the difference between an idea and a material object, a material body? The old physicists called them bodies. We call them maybe objects today. What's the difference fundamentally between an idea and a body? Anybody? Well, first thing is that bodies are statically conceived. They don't involve any motion whatsoever. So my water bottle, it has a structure to it. It generally has a surface that defines it, that separates the outside from the inside. And you can really put a line that's tangential to the surface at any point, and it will always point inwards towards the center of the body. But the fundamental defining feature of of bodies is that they're static. They don't involve motion. Ideas, on the other hand, or concepts, relate bodies to one another. It could relate the body to itself. For instance, this body has been in this position, now it's in this position. So now I've introduced motion to the presentation. So motion, something moving, is a conceptual entity, right? You have to have a memory of where it was before in order to even perceive that it's moving in the first place. So that's one degree of abstraction, is taking a physical body and moving it. It's the most basic idea imaginable in some sense. Now, I can take that motion and I can take it and relate it to other motions, and now I'm getting into second order, third order degrees of abstraction. But it's a rational presentation still, because I started with an actual body. I was talking about it moving. Now I'm talking about, when I moved my water bottle earlier, I moved it slower than I moved it just now, right? So now I'm relating two different motions to each other, but they're still rational because they terminate in a material body that's actually doing motion. And so what you'll find is that all rational thought terminates on something, some sort of material actor that's in motion, essentially. They'll all terminate in basic motions. Now, the problem is these particles of subatomic physics, they start out as motions, okay? There's no actual material body in action at the heart of these subatomic particles. This is a serious problem, actually. I think this leads to an unending amount of confusion, because it's very easy to treat these activities, which we call particles, as if they're material bodies. And we start moving the activities around. And we start slamming the activities into each other and absorbing the activities. And we get into this state where we're not really sure what we're talking about at the end of the day, except we have equations that describe those behaviors really, really accurately. And that's good enough for inventing technology, and so we forget about it. But it's a little bit tragic, because our job as scientists or philosophers, whatever you want to say, for whatever reason, by the way, when I graduated from school, they didn't give me a doctorate of science. They gave me a doctorate of philosophy. Scientists all have doctorates of philosophy, which is very bizarre if you think about it. So our job is to make sense of the natural world. The engineers can go and build stuff, right? That's great. They're really important people in society. But as scientists, right, as astronomers, astrophysicists, we have to think about what these things really mean. And the fact of the matter is, down at the level of the atom, things turn into math equations really quickly. And that's, like I said, that's extremely propitious for building technologies, but it's really, really painful in terms of understanding what the atoms are actually doing. So we do know a few things, though, about the atom. We know that the atom is essentially a harmonic oscillator, right? It's almost like a little droplet that vibrates, right? It pulsates. And so the simplest atoms, this, by the way, is a periodic table, just like the one behind here. Same thing. But it's drawn in terms of what new vibrations the atom encounters as it gets more material added to it. So as you fuse up in let me take a look at this thing. Upper left-hand corner, we have the simplest atom, hydrogen. Now, hydrogen can only really vibrate in a few different ways, right? You can only take that sphere and jiggle it, I think, essentially like this, just like uniformly. You pulsate it, right? And so the hydrogen has different energy levels. They'll say it can go and it can vibrate more or less, let's say, or faster or slower. There's no way to separate that out. But as you get more material agglomerated on, you start getting these new vibrations that appear. These are, you can essentially think of these as being stacked on top of one another. So as we move down the periodic table into the metals and so forth, you actually have to add on these extra lobes onto the atom. So it starts getting these new surfaces which appear. And they're really cool because these new surfaces allow the atom to essentially interact in new ways. And you can build complex materials, you can build lattices, right? You can bond things together. You can develop a situation where some of these orbitals, some of these surfaces are maybe used in bonding you inside of a lattice, but some of them are used for magnetism and conductivity. So you take on all of these new attributes. But the basic idea here that's been developed by the chemists and by the quantum physicists to some extent is that the atom has this vibration. It can be described as a wave equation. What is it that's vibrating? Well, it's the electron shell, right? What is an electron shell? What is an electron, for that matter? That's the next reasonable question. We talked a little bit about this last time when we were trying to talk about electromagnetism and conductivity and so forth. But again, the electron, it's a particle, right? It's a subatomic particle. What is a subatomic particle? Well, it's something in motion, but we don't quite know what that something is yet. It's completely undefined as far as science is concerned at this moment. It has intrinsic momentum. It has a motion. It even has a symmetry to its motion where it can rotate twice before it comes back to its starting point. What does that mean? What is the shell doing? Well, it's up to us, to our imaginations, to process what it could possibly be doing. But there's some freneticism to it. And the chemists seem to really understand that the surface of the atom, that the electron represents the surface of the atom in some kind of motion. And so all of these shapes that shell can take on have to do with the particular vibrations of that surface and whatever sort of material it's made out of. Well, clearly it must be made out of some sort of subunited material because it's impossible to deform something without subunits, right? There's no way to get a perfectly rigid, solid object to deform. It has to have smaller pieces to it. So there's some sort of fiber or whatever from which this electron shell is made out of. From a scientific standpoint. From an accounting perspective, we think of these in terms of electrons because the electron is the quantity of motion that's contained within essentially one wave of light that excites a vibration out of that shell. It wiggles, right? And light can actually wiggle it perfectly. There's a correspondence that's quantized, and we call that amount of motion the electron. So the electron is a subatomic particle. Subatomic particles are not material bodies like my water bottle. They represent some activity that's occurring, right? They have energies to them. They have motions inherent in them. They have momentums inherent in them. They have, angular momentum, so they have some sort of rotation. So, right, there's a lot of information there in this word particle. It's like a set of information that tells you about something that's happening, but you don't really know who the actors are, which is a little bit bizarre. Okay, so let's take a look at the key players in the nuclear reactions that we need to familiarize ourselves with. The proton, the neutron, the electron. Those are the first ones we should deal with. Okay, so we talked a bit about the electron. It's the outer surface of the atom. What's up with the proton? Well, the proton is thought to represent the nucleus of the atom, so the central point within it. The charge of the nucleus, so the motion, let's say, of its outer surface is directly opposite that of the electron. It's positive, let's say, with respect to the electron's negative charge. Now, we talked a bit about charge before. I made a case for you that I think that a good way of visualizing charge has to do with the directionality of the motion of the surface of the atom, particularly with respect to a hydrogen atom, how that electron shell is twirling perhaps and involuting. Because I think that you can visualize the motion of the electrons, which is called spin 1/2, if you think about the surface turning twice and involuting as it does that. So it's churning through the poles and back out the bottom. You will get a spin 1/2 motion that way. Well, the proton should be at the center. It should be doing the exact opposite. And so that's one way to think about it. These effective masses, by the way, that you see written in your textbook, I touched on that briefly before. These are equivalent masses, right? This is how much the strength of the magnet applied to a stream of these charged bodies is going to be needed in order to deflect them some amount. And so it's an equivalent mass. Mass, of course, is originally defined in terms of gravity. It's how much connection you have to your environment gravitationally. And then the neutron. The neutron's really, really interesting. So neutron's another one of these subatomic particles. Of course, these are all subatomic particles, which means, again, some sort of action, right? Action of what is a little bit up for grabs beyond the electron. The chemists understand the electron is the action of the shell of the atom. What about the neutron? The neutron's really, really weird. So let's see here. The neutron, it seems to have the same deflective strength, the same mass as the proton, right? Which is, by the way, most of the mass of the atom. The electron itself seems to have very little deflection strength in isolation. So neutrons are weird because what happens in these chain reactions is that you can force these neutrons, Let's forget about fusion for a second. Let's talk about fission. So the opposite side of fusion is when atoms fall apart and make two atoms. And there's some high energy things that are released. One of the ways they fall apart is they emit neutrons. Neutrons pop out. Now, the weird thing about neutrons is that after something like 15 minutes, a neutron will just spontaneously decay into a proton, an electron, and another piece of another particle called a neutrino, which we'll deal with in a moment. The funny thing is, what's a proton and an electron? By accounting measures, a proton and an electron is essentially a hydrogen atom. So neutrons seem to basically turn into hydrogen atoms, right? That's really, really interesting. You know, and there's been a lot of debate over the years. So there's this gentleman named Prout who started thinking about how you could basically look at the periodic table and you could build each element by just squishing together a bunch of hydrogens. He started thinking about, it's called Prout's law, which is the idea that all of the elements are essentially just built like Legos out of hydrogens. So if the neutron is something like a not fully formed hydrogen, it would make sense that when you slam neutrons into other atoms, as we do in some of these reactions, these fusion reactions, that they would take on that same mass, the same level of connectivity. They get all of the material of a whole hydrogen almost, right? Very, very similar. Now, what's up with this neutrino business? The neutrino is an interesting thing. So again, subatomic particle. So it's some sort of motion, some sort of activity that happens, that propagates in the system. What happens is when you squish two atoms, two hydrogens, let's say, together, what happens is that you get this new atom, and you get a little bit of excess relaxation in the system. The reason they came up with this idea, I think it was actually, I think it was Wolfgang Pauli, who decided to name this extra energy that was left over, this extra relaxation in the system. And he called it the neutrino. And that's where we got that idea from. Now, there's various ways of detecting that at this point. The neutrino is kind of interesting. It doesn't have the same symmetries as light, so it's not exactly like radiation, although it propagates similarly. It's much closer to electricity, actually. It has the same spin qualities as the electron. So it's something more like a chain reaction amongst atoms, one-on-one. It's very interesting stuff. So I think that we can move on to the equations a little bit. So, you know, I won't spend too much time on this because you guys are probably not going to remember these after this course anyways. The idea is that the nucleus, I think I've kind of beat it over the head. When you squish these things together, you actually end up with less mass, right? And as a result, you've accelerated the material in the surroundings at some speed, which is moving at its maximum deformation speed, the speed of light. This is called binding energy, by the way. I need to go back to this. By the way, this is kind of like a nice visualization of how I like to think about atoms. They have this nice shell to them, and there's some sort of rarefied portion of their shell. And we know this from the radial distribution function of the electron wave function, that electron extends indefinitely into space, right? Remember, when you look at the location of the electron, you're going to mostly find the electron right next to the nucleus. This is the nucleus. And then you're going to find that there's some chance you're going to find the electron far away from the nucleus. In fact, there's no limit, theoretically, on how far away the electron can be from the nucleus. So maybe some of the electrons in your body are essentially, at the wall right now or something, until something intercedes, right? So I like to visualize the atom as having some thinned radial portion to it, which is far away from the actual shell. It gets ignored in most depictions. At any rate, the textbook says this: if particles come together under the strong nuclear force and unite to form an atomic nucleus, some of the nuclear energy is released. The energy is given up in a process called the binding energy of the nucleus. Okay, so that's what we're talking about here. We're talking about this relaxation event that gives some motion back into the system by squeezing these atoms together. Now, how do you actually get two atoms close enough together that they want to actually join their surfaces, right? Generally speaking, we know that similarly charged surfaces don't really like to stick together, right? It's how do you get two electrons with the same surface motion stick together? It's not easy to do. They're going to repel each other. They're going to be pushing against one another. Their surfaces are just trying to bat against one another. All of that motion is trying to push them apart. Basically, the only way you do it is where you have extraordinary pressure from all sides, like you do down in the core of the sun, in the core of all the stars, really. You have all of these atoms pulling on one another. It's sort of like, you guys ever see these horrific stampedes at these football stadiums in Europe and stuff? It's like, or at these rock concerts or something. It's like the people in the middle, sometimes they just get squished, right? Because everybody's kind of pushing, and the people at the center take all the force of everybody pushing. It's the same thing happening inside of these stars. And so the idea is that the stars are the only place where we would ever have enough force, enough effort, enough pressure to actually get two atoms close enough that their surfaces would dissolve and they would become one. This is a very unfavorable situation normally. And so it seems like you need something by the way, pressure, temperature, very tightly related, right? So when we talk about something under great pressure, like at the center of the sun, think about those pistons in your engine, right? They're compressing things. It's getting hot. And so the temperature necessary to fuse just two simple hydrogens is something like 12 million Kelvin, which is just an inconceivable temperature, like vaporize you levels of temperature. It's hard to even imagine those kind of temperatures. Let's see if I guess they can get even hotter though. So regions near its center, the temperature in the sun raises to up to 15 million Kelvin, which is pretty crazy. It looks that almost all of the sun's energy is generated within a small radius, 150,000 kilometers of its core, which is about 10% of its total volume. So just a little nucleus in the middle is where all of this is happening from. There's another possibility too, and I'm going to save it for next class, which is, and I touched on it a little bit last time, and I'm going to just keep reminding you of this, which is called lattice-confined fusion, which there's a couple of NASA white papers on this. It's quite a promising idea that if you have something more liquid or solid, you could actually squeeze atoms in between the layers of that lattice with much less energy at lesser temperatures, right? And why am I even bringing this up? There's one star in particular, and there's a few stars that we know of in the universe that don't totally make sense. There's one called Cebulski's star. I couldn't tell you exactly where it's located off the top of my head. And I'll come back to this again. I'll show you guys some pictures next week. But Cebulski's star is really interesting because what they've seen in Cebulski's star is that they get light signatures that show that there are heavy elements that are decaying in the outer layers of this star, which by itself wouldn't be that interesting. What's interesting is that those heavy elements are only stable for something like 15 minutes. So how do you get the production of a really big atom that only lives for 15 minutes at the surface of a star? It's a very good question. It seems like there must be some alternative fusion pathway possible at the surface of that star. Now, it's funny, if you go and read about Cebulski's star on Wikipedia, the answer that they go to is aliens, actually. They're like, well, aliens are dumping their trash in the star. Maybe, but maybe there's some other way that fusion's happening, not just in the core of the star, but actually throughout the star. Maybe if we have misapprehended the lattice, maybe if there is actually a layered onion-like structure to the sun, and we have the potential for some liquid or condensed matter materials, you can actually squeeze atoms between those layers, like in a press. And you can actually do fusion in the outer layers of the sun as well. So that is a completely fringe idea, but I think there's some interesting, tantalizing evidence that something like that must be happening. Anyways, so this is the most simple, this is the basic fusion pathway for our sun. You got these simple hydrogens, right? These light, basic hydrogens, they're squished together. They make a heavier hydrogen, which is quite interesting. This thing is said to possess a neutron. Again, these subatomic physicists are not really interested in material of like, well, where does the neutron go? It doesn't really just like sit in the center floating all by itself, but it doesn't matter. It absorbs 1 neutron's worth of material in motion, okay? So it's a heavier hydrogen up there. You also get this backwards spinning electron business, which is the positron, the E+, and then we get this neutrino, the V, right? So there's some excess energy that's released into the system from that. Now what you can do is you can take that heavy hydrogen, you can smash it together with another light hydrogen, and all of a sudden you get a helium. You also get some radiation that results from it, right? So as that network relaxes, there's a serious burst of energy throughout the system, which we call gamma radiation. You can also take 2 of those heliums and smash them together and get a heavy helium, plus a hydrogen, plus a hydrogen. These are the basic chemical reactions that are occurring at the heart of the sun, as far as we can tell. Because there really isn't much in the sun besides these 2 elements. There's some other trace stuff, right? But it's thought that it's been grabbed up from other stars. In fact, it's believed that our whole star system, well, everything here, is the result of multiple suns that have already burned out, and we're in at least a second, probably 3rd or 4th generation star system right now. Because, quite frankly, these big things, these big elements, especially iron, tin, even carbon and oxygen, we're not going to get those from a star like ours, right? It's just not big enough. Our star is pretty small, honestly. It's on the tiny end. There's certainly many more that are smaller than us, but it's not big enough to make very big elements. It can only make these little guys. All right. This is just a different picture. Not sure how useful this is. Maybe this is a better way for you to think about it. I don't know. Okay. So I'm going to wrap this down for you. First of all, anybody have questions? I know I've thrown a lot of technical stuff at you today. And I apologize for that, but we just don't, I'm trying to catch up in some sense because we missed a class already, and we do need to make our way towards cosmology by the end of this. So, questions? I'll ask you again at the beginning of next class. All right, let me try to put a bow on this for you. The stars in particular, our sun, understanding how it works, what it's made out of, they really matter, and they really matter to us in a purely, not just a metaphysical sense, but in a technological, very real sense, right? We're tired of burning stuff here on Earth. We're tired of combustion engines. Most of our money goes towards energetics, right? If you ask yourself, why does my groceries cost this amount of money? Or why do my things cost this amount of money? Most of that money is energy costs, right? Transportation, paying to keep the lights on at factories, to program the robots to assemble the things for the most part. Energy is really, really at the heart of everything we do on Earth. The sun seems to be some sort of incredible powerhouse. That's pretty much goes without saying, right? It's the source of all of the light that we get, aside from these, although we wouldn't have been able to build these without sunlight in the first place. It's the source of everything powerful. And it's been perceived that way since antiquity, right? The ancients all realized the power of the sun. So we gotta understand how this thing works, and we gotta understand it a little bit better because some things don't totally add up about it. And I think that as we understand the stars better, we'll be able to more effectively instrument its power in our own processes here on Earth, which I think is going to lead to a much more peaceful, less oppressive, and cleaner Earth, which is what we really want. right? To do that, we have to be careful. We have to approach science, that is the mechanistic understanding of nature, really carefully. We can't just throw words around like everybody knows what you're talking about. Words like energy, words like particle, right? You know, you can make your way through a PhD in sciences and not have a firm, consistent usage of those words and understand what they mean. And that's really troublesome because people go out and they start working on things using old ideas that they inherited from their, people in the 1800s, and they're not totally in tune with what they're talking about, even though they'll throw these jargon terms around. So a huge part of us being able to understand the sun, being able to move towards a better future, is being able to use language really consistently and being able to make sure that we're talking about the same thing when we discuss these ideas. So energy, it's material in motion. Particles are activities, right? They have predictable measurements of these particles. You know what extent, what quality, quantity of that action you're going to get in each one of these cases. But they seem to be telling us something about the material atomic landscape that's down there below the wavelength of light, below where we can actually see. The atoms have some material substance. It's doing something. All of those actions at different parts of the atom are responsible for all of the amazing things that we see in our world. And at the level of the sun, from the light to the fusion at its core. So next time, what we're going to do is we are going to start looking at the signatures that come from the sun, that come from other stars. We're going to start looking at the different types of stars and how we know what we know about them based on examining their light. But remember, light is all we have. Light is some sort of activity, some sort of conversation between atoms, the specifics of which are still a bit nebulous, and so there's a lot of work to be done. But we're going to use that conversation and we're going to decode it, and we're going to listen in, and we're going to try to make sense of what the heck all of these different stars are doing and what it says about our own star system in the future. So anyways, thank you guys, whoever came this morning. I really enjoyed meeting you guys, and let's do that again next week. Otherwise, have a great week, and I'll see you guys, or weekend. I'll see you guys Tuesday.